So this is the start of logs. In order for you to understand logs well, you should know your exponent rules. So a log is just another way to write an exponential expression. It allows us to write it in a way that we're able to solve for an unknown exponent. So we read it log base b of a is equal to 0. And the base in the log is the same as if you would write it in exponential form. Now, if you have a log base e, we don't write log base e, we write natural log. So natural log is just log with a base e. Sometimes it's easier to write it as log base e when you're following your rules or expanding and condensing, but we would never write log base e in a final answer. We'd write natural log. And E is just a number. It's Euler's number, and it's approximately 2.718. You can throw it in your calculator. It's there. All right. So when you are in log form, something that looks like log base b of a is equal to x, we can rewrite this in exponential form. This, like I said before, is still your base. It now becomes raised to the power of x. So b raised to the power of x. We roll through the equal sign, and that is equal to a. So these two expressions are equivalent to each other. So anytime we roll our log, we start with the base, we go across the equal sign. So log base b of a is equal to x. You can go in either direction. Just like when you write x and we know there's an exponent of 1 on it, if we have a log without a base, it is base 10. So if you are given something that would look like log base 4, we would actually know in our heads that this is log base 10 of 4 is equal to x. So when b isn't given to us, we know that it's a 10. Okay? All right, so let's just rewrite from one form to the other. So here we're given exponential form. So we have our base. We always start with our base. And then we're going to roll through that equal sign. So we have log base 2 of 16. We roll through that equal sign to 4. Same thing in our second example. We have 3 to the third is equal to 27. So we have our base of 27. So log base 3 of 27. And then we roll through that equal sign. Equals 3. This would be a good time for you to pause. See if you can do the next two on your own. So like you can see in that last one, it doesn't matter if the numbers are positive, negative, fractions. We still are just moving them from one spot to another. Now, if you're given a log form and you need to go into exponential form, we still start with the base, go across that equal sign, and roll through your equal sign. So 2 raised to the first power is equal to 2. I'll show you another one. 4, the base, raised to the second. Oops. Let me try that again. So we have 4 raised to the second power. We roll through the equal sign to 16. And you can see now that you're in exponential form that, oh yeah, that makes sense. We know 4 squared is equal to 16. Okay. So here we have log base 11. So base 11 raised to the negative second power is equal to 100, 1 over 121. In the next example, we have one with a log base not listed. So if you need it, write the 10 there so that you can see it. And then we would say, hey, 10 to the third power is equal to 1,000. And last one, again, doesn't have that base 10, but we can still write it. You should be very comfortable going from one form to another form. Now, why do we do that? We do that so that we can solve. Anytime that we have an unknown exponent, we can rewrite it in logs, or sometimes just writing a log into an exponent helps us be able to solve. So here we have base 5 raised to the second power. We roll through that equal sign, and it is equal to this whole entire piece here. This is now something we know how to solve, because we know that 5 squared is equal to 25, and then it becomes a pretty easy little equation that we can solve for. Again, a good time to pause, see if you can do the next two on your own, and then go from there. In order to do B, you have to be comfortable rewriting rational fractions, which means, rational exponents, which means your exponent is a fraction, into a radical form. So the root is on the bottom, so that goes up front, and then the top number stays as an exponent. All right, here we don't have that base of 10, so we can write it in if we want. And then we have 10 to some power. Oops, too many zeros. Try again. There we go. Okay. And then 10 to what power gives us 10,000? Well, there's 4 zeros, so it's, So it's 10 to the 4th, so we know x is equal to 4. And we want to remember that we're solving for the variable, so we need our final answer to say x is equal to 4. All right, so let's take a look at the graphs. We have two graphs. We have a graph of a log, just general parent function graph, and then we have a graph of the inverse, which is our exponential graph or an exponent. So log graphs continue to increase as we head towards infinity. You can see that the graph doesn't exist here. It doesn't exist when we are less than 0 or even equal to 0. We have a vertical asymptote at 0. Okay. On the inverse side of things, we can see that our exponential function is growing really, 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 really fast. And our range, again, goes from right above 0 all the way up to infinity. We now have a horizontal asymptote happening. All right, so this is our log function. So we would say f of x is equal to log base b of x. Our domain, we are starting at 0, but we are not including 0. And then we're headed off to the right to positive infinity. The range, we're starting at negative infinity, and we're just going to keep going up, up, up. We don't go up very fast once we are into our positive numbers. But we are increasing nonetheless. We have one intercept where we go through the x-axis right here. We have one intercept, and that intercept is at the point 1, 0. And because we have that vertical asymptote happening, we never touch the y-axis. So we don't have any y-intercepts. So we have an intercept of 1, 0. This is our x-intercept. And we have none for the y-intercept. We have one asymptote. It is at the line x is equal to 0. Just remember, we always write asymptotes as lines. They are not just a number. All right, on our exponential function, we would say this is the parent function f of x is equal to our base raised to some unknown variable. Our domain, remember domain and range of inverses also are inverses. So the range of our original becomes our domain, and the domain of our original becomes our range. Those go in both directions, but we do not touch the x axis at all because we have that horizontal asymptote at y is equal to 0. So our x-intercepts, this time there are none for the x-intercept. And our y-intercept is the inverse. So we have an y-intercept at 0, 1. So those are your two graphs. If you wanted to, we could add on that intercept here at 0, 1, and we could say, hey, we have that horizontal asymptote. All right, last thing is the domain of log functions. And we just kind of talked about this with our graph. The domain has to be positive. So if you are taking your function whatever is here has to be greater than 0. Okay, so if there's like a little expression there, we're going to set it greater than 0 and we're going to solve it. So let me show you an example. We don't care about the base at all. We are just caring about this x plus 3 part. So that is in that spot of x. And we're going to say, hey, this has to be greater than 0. So in order for this log to exist, the x values that you're plugging in to evaluate have to be greater than -3. Let me show you another one. So here we have 4 minus x, and that has to be greater than 0. So let's add our x to the other side. So in order for this log to exist, x has to be less than 4. When you're asked to write your domain in interval notation, we would say, hey, we're going from -infinity to 4. And it does ask you to write your answer in interval notation. Go back to this one and do that. Okay. Here we have a binomial squared that we have to say, hey, is greater than or equal to 0. So if just one of those binomials is greater than 0, then we're good because they're the same. So our domain would start at -2, head all the way to positive infinity. The only time domain gets a little involved is if it is maybe something like this quadratic that we're going to have to factor. Notice here that there is no base given on that log, but we remember that that's base 10. All right, so in order to solve this quadratic, we're going to factor it. We're going to get our two critical values. So we know that x is equal to 5 and x equals -4 are our critical values. When we take our critical values over to our number line, we know that this quadratic is opening up and then crossing the x-axis at those critical values. So when we're looking at where are we greater than 0, we are greater than 0 here because we are above the x-axis, and we're greater than 0 also here because, again, we're greater than the x-axis. So in order for our domain to stay positive, the x values have to be from -infinity to -4, or they have to be from 5 to infinity. And again, we're not going to include -4 or 5 because at those points we're equal to 0. And if we go back to our definition of the domain, that x value has to be greater than 0. It is not allowed to be equal to 0. So that's your intro on logs, how to go from one form, exponential form, into log form and back, and what the graphs look like and the characteristics of those graphs, and then also a review about the domain of logs that have to be greater than 0.